let's go and have a look and see how we differentiate these trig functions. To start off with, have to look at a few ideas. What's known as small angle theorems. So when you talk about very small angles, so as x is approaching 0, and from the graph we can see these limits quite easily, that sine x is also approaching 0, cos x would be approaching 1, tan x would be approaching 0. I don't think I end up using all of these, but they'll come in handy. So what I'm now going to draw is a circle, and we're going to compare the area of the sector AOC, which we know is a half r squared theta, which in this case I've labelled x. But I know that that area is going to be bigger than the triangle, but it'll be smaller than that right angle triangle. If I was to draw a tangent at A, that would be a right angle triangle because radius is perpendicular to tangent and so on. So I know I can trap the middle area. So half AB sine C, so area of the triangle, less than half r squared theta, area of the sector, and then half base times height for the right angle triangle, tan x. Now, I'm not really interested obviously in the halves. What that gets me is this idea that x will always be in between the value of sine x and the value of tan x. And then I'm going to divide everything by sine x. If I do that, I get this interesting relationship. X on sine x is in between 1 and 1 on cos x. But I'm interested in really small angles. So as x approaches 0, cos x approaches 1. And so 1 is both the upper bound and the lower bound. X on sine x is in between 1 and 1. Well, that now tells us what the limit of this interesting fraction is. That tells me the limit as x approaches 0 of x on sine x is 1. Another way of putting that is for very small angles, sine x will actually equal the angle itself, as long as we're dealing with radians. Because x on sine x is equal to 1, so the numerator would equal the denominator. So for very small angles, we can approximate small angles with using what we call this small angle theorem. Instead of finding sine x, we can use x. But this limit of x on sine x, it's a 3-unit limit, and they do like asking questions on finding things like this. So it's usually just a 1 marker. It might be a multiple choice or just a quick question to start off with. But they'll say, oh, what's the limit as x approaches 0 of 5x on sine 5x? The key is making the numerator in this case the same as the angle. And in this case it is. So I don't have to do anything. So I know, oh, that's 1. Okay. Because if x approaches 0, 5x obviously approaches 0 as well. Whereas if I got something like this, x on sine 3x as x approaches 0, I want to make that 3x on sine 3x. So I'll multiply by a third. I know the fraction, 3x on sine 3x, that'll approach 1. So I get a third times 1, which is a third. So the key to using that limit is that the angle will be the same as the numerator. Of course, it could be the denominator. There's no reason why we couldn't have the reciprocal, because the reciprocal of 1 is 1. So you could also say sine x on x rather than x on sine x. All right, but that limit I'm going to use to work out the derivative of sine x. We're going to go right back to first principles. So the limit as h approaches 0 of function x plus h, so sine x plus h, minus sine x all over h. But I can expand out the sine x plus h. Sine cos, cos sine. If it's the sine, it's the sine. Right, but this is as h approaches 0. So I'm going to break this fraction up a bit. I'm going to write it as cos x times sine h on h. So that's just the middle bit. I can handle that one all right. Because as h approaches 0, sine h on h will approach 1. I know that. The other one, I get sine x times cos h minus 1 over h. So I'm going to have to play with this one a little bit. So I rewrite cos h using double angle theorems. Now, cos h is the same as 2 cos squared h on 2 minus 1. Cos 2 theta. And we have 3 choices. Yeah? One of those choices was 2 cos squared theta minus 1. Effectively, that's what I've used. Instead of 2 theta, I've got h. So therefore, when I go 2 cos squared theta, which is half of 2 theta, I now go 2 cos squared h on 2, half of h. Minus 1, but we also had another minus 1, so we get minus 2 on top. Alright, now I'm going to rewrite that. Okay? Because of course, cos squared minus 1 is sine squared. So 2 cos squared minus 2 is 2 sine squared. So I'm almost there because I'm trying to get to this sine h on h relationship. Okay. If I now rewrite that, instead of writing it as, let's go back, 2 sine squared h on 2, but I write it as sine squared h on 2 over h on 2. Because I did have, if you like, it multiplied by 2 on h, which is the same as dividing it by h on 2. Almost there, because it's sine squared. So now I break the sine squared up into sine h on 2 times sine h on 2. I can now use my limit. Because as h approaches 0, the sine h on 2 becomes 1. But then when I substitute it into the sine h on 2, I get sine of 0, which is 0. And we're just simply left with cos times 1 plus sine times 0, cos x. Now, of course, the good news is you obviously don't have to derive that every single time. That's the whole point of first principles, so we can come up with the formula. All we need to know is, if we have the sine of some function, if I want to differentiate it, basically you differentiate the angle, it'll go out the front, sine will go to cosine. The sine becomes cosine, and the angle does not change. Alright, let's see what happens with cosine. This is going to be a little bit easier. Now that we know how to differentiate sine, because I can change cosine into sine. Remember, they're complementary ratios. So cos of x is the same as the sine of pi on 2 minus x. We now know how to differentiate that. We said we differentiate the angle. Well, if I differentiate pi on 2 minus x, I get negative 1. Sine goes to cosine, the angle does not change. But the cosine of pi on 2 minus x, complementary ratios, is sine x. When you differentiate cosine, you get minus sine. So cosine function x minus the derivative times sine function x. Alright, let's have a look at tan. Tan, I can rewrite as sine on cos. And I now know how to differentiate both of those. I'm going to have to use a quotient rule. Square the bottom, cos squared. Write down the bottom, cos. Diff the top is sine, differentiate sine, we get cosine. Minus, write down the top, sine, differentiate the bottom, cos. Differentiate cos, I get minus sine. So on the top we get cos squared plus sine squared, which is, so we now have 1 on cos squared. The reciprocal of cos is secant sec squared. So tan becomes sec squared. So when we differentiate tan, again, differentiate the angle, goes out front, times by sec squared of the angle. Alright, let's look at some examples then. So if I have to differentiate the sine of x cubed differentiates 3x squared, sine goes to cos. 3x squared cos x cubed. Tan of 1 on x, differentiate 1 on x, you get minus 1 on x squared. Sec squared, tan goes to sec squared, and the angle is 1 on x. The log of the cosine of x. So it's actually a log function we're differentiating. Differentiate logs, derivative on function. The function in this case is cos x. So the derivative of cos is minus sine. on the function cos, I get minus sine on cos, but of course sine on cos is tan. So the derivative of the log of cos is minus tan. Tan to the power of 5. So this is like a chain rule question, it's just that we haven't got the parentheses there. So bring down the power, 5, lower the power, 4, diff the inside, well inside is tan x, it's tan x to the power of 5. Differentiate tan, we get sec squared, so I get 5 tan to the 4 sec squared. The swimming question. Cosy. Yeah, because when you go swimming, you wear your cozies. Okay, now, so it's the cos of e to the x. We differentiate the angle. The angle in this case is e to the x. Differentiate e to the x, you get e to the x. But cos goes to minus sine, and then the angle doesn't change. So it really is the swimming question. Because you ever notice how when you go swimming, you get the sniffles? And of course, how do you cure the sniffles? You use sine x. See? So, you go swimming in your cozies, and then you get sine x to... Alright. Okay, that'll do us. Enough of my very lame jokes.